geroscience as a new paradigm. If you were to tell somebody in the turn of the 20th century that, hey, you know those set of diseases everyone's dying from right now, bacterial infections? Well, in a couple decades, almost nobody is going to die from those in the developed world. Nobody would have believed you. And yet, that's what happened. And so, to use Aubrey's term, hopefully we can bring aging under medical control, this century. We can do that in part because of advances in the basic biology, the hallmarks of aging, the 7 deadly sins. Here's some of the underlying mechanisms that many of you know. This is a little out of date. There are probably about 100 interventions, genetic and pharmacological, that extend healthy lifespan in mice, and we just need to translate these into the clinic. Here's some of the quantum of lifespan extension of these various interventions. I am partial to heterochronic bone marrow transplant. I'm going to talk about that at the end. So this is probably my most important slide, which is when we make the case to investors or founders or governments or anybody, why will long bio be more effective? Why will it have a clinical success rate that is higher than the traditional pharma model? And part of the answer is, in the traditional pharma model, we're highly, highly reliant on these contrived, unrealistic animal models of disease. Jack Scannell has written in Nature Reviews Drug Discovery on this predictive validity of these models. So basically, when you have a really good model, like, for example, bacterial infection in mice, very quickly thereafter, you develop effective drugs for it. The way to basically have job security as an animal model of disease is to not work very well, like Mouseheimer's, the amyloid beta mice or the tau mice. People keep banging their heads against the same wall and going nowhere. So a partial solution is, with long bio drugs, geroprotective drugs, we test them across species, yeast, worms, flies, mice, fish, et cetera. And if they extend lifespan and robustness across these species in a non-contrived, wild-type normal model of aging, that's much more likely to work in the clinic and to be a pipeline in a pill. So we'll talk a bit about one of my favorite interventions, which is bone marrow rejuvenation. So your whole immune system, it starts in your bone marrow, the hematopoietic stem cells, and it gives rise to the white blood cells, red blood cells, et cetera. And we're working on rejuvenating the bone marrow stem cells, as well as T cells, within a company called ImmuneAge Bio, which launched pretty recently, a little over a year ago. So I'll just very quickly go through some of these points in the interest of time. But if you're an investor, get in touch because we are raising capital. We're raising our second round now. So I already spoke about how aging is the #1 risk factor for age-related disease. We think that targeting the bone marrow stem cells is going to be really effective, in part because we can take these cells out of the body, rejuvenate them ex vivo, and then reinfuse them. And so you can see the HSC here is at the apex of this lineage of all of these immune cell types. And there's been a lot of interest, even revolutions, in cancer care, autoimmune disease, et cetera, by targeting individual ones of these immune cells, like T cells or NK cells. But what if we actually just rejuvenated the source of all of those various immune cell types? So some of the research that turned me on to this approach a couple years ago is the young to old bone marrow transplant field. So you can transplant young bone marrow into an old mouse, and it will live up to about 30% longer. It slows aging in every way that we check. It even enhances memory and learning, which I wouldn't have expected, a younger immune system enhancing cognitive function. And Aubrey has also, at the Lev Foundation, tested young to old bone marrow transplant under a similar paradigm. So we don't have clones. We don't have younger clones of ourselves, at least not yet. There are people working on that, to transplant bone marrow. So the next best thing would be to rejuvenate our own bone marrow, ex vivo and in vivo. So ImmuneAge is built on 2 platforms, 2 pillars. The first is stem supply, where we can achieve a 1,000-fold expansion of HSCs. So the world record before was about 10 or 20x. This work comes out of Stanford and Oxford, and the team got 2 Nature papers on this. This alone could be a breakthrough in the bone marrow transplant field, where 50% of patients die on the wait list. They don't find a genetically matched donor in time. But for the first time ever, this expansion capability allows us to screen drugs in HSCs at large scale, because you previously couldn't get your hands on enough HSCs because they're a very rare and precious cell type. We've also developed a computational platform to classify old, young, and rejuvenated HSCs and T cells. And then the second pillar is age screen. So we basically look at various hallmarks of aging to rejuvenate these cells, to find cocktails that ex vivo and sometimes in vivo rejuvenate them. Right, so this is the basic overview of the computational capacity. We take various omics tools, we plug it into standard deep learning capability, and then we classify those cells. So we're developing 3 products right now. Sorry, the formatting is a little messed up here. The first is a small molecule, a pill, that rejuvenates the immune system. We published an analog of this in Nature Aging last year, and we've shown that it enhances immune function in cancer models, infectious disease models, et cetera. And it's very safe and well tolerated. This is convenient because it's a large market. You know, there are all kinds of neglected diseases all over the world, infectious diseases, where if we had a host-directed therapy that would boost immune function, that would be very helpful, especially if we have another pandemic, which is inevitable eventually, to have a pill that we could take to mitigate COVID 2.0. The second program is ex vivo rejuvenation. We take out your cells, we rejuvenate them in a dish, we put them back. And the third is HSC expansion, where we increase the number of those cells, which is the #1 factor determining bone marrow transplant success. So some of the work we've done so far, we published one of these molecules in Nature Aging. This is an enhancer of mitophagy and mitochondrial biogenesis. This is, to our knowledge, the most potent rejuvenator of the immune system yet published. We've developed a platform to test a lot of these different mechanism of action rejuvenators ex vivo, and our collaborators have published 2 Nature papers on the HSC expansion work. So what clinical indications should we go after with immune rejuvenators, small molecules, and ex vivo immune reboot? Long-term, everybody on Earth can benefit from this. This is why I'm doing this. It's not for the money. It's because I think that HSC rejuvenation is the lowest hanging fruit, most likely to work intervention in the near term. In the near term, also, we can go after respiratory tract infections. So this is the 4th leading cause of death globally, and it's neglected in the developing world. Another application is patients receiving chemo. So when you get chemotherapy, it kills off your fast-dividing cells. The fastest dividing cell type in your body is the HSC. And so the dose-limiting toxicity in chemotherapy is myelosuppression or anemia. So we could go up to a higher, more effective dose in cancer patients if we could set aside or bank some of those HSCs before they get the chemo. Then the HSCs dodge the bullet, and then we reinfuse post-chemo, preventing the long-term negative effects and accelerated aging of chemotherapy. Bone marrow transplants, also a large area. We can improve vaccine response in the elderly. There are many other immune suppressive conditions. And there's also data in the literature that HSC aging drives atherosclerosis and dementia and many other age-related diseases. So what is the long-term vision? We aim to have this simple outpatient procedure, it takes a couple hours, where we basically mobilize the HSCs in the peripheral blood with injection of 2 molecules. This is routinely done all over the world in bone marrow transplant setting today. We apherese them out. We expand them with stem supply. We rejuvenate them with these cocktails. We reinfuse as needed, and we bank for later because no one's getting any younger. And the analogy to take with you is the ship of Theseus. So it's this ancient Greek myth about the concept of continuity. If you slowly replace some of the wood in the ship, when do you declare that you have a new ship? And that's what we aim to do, is gently, gradually replace the immune system.